In this session, we'll look at the log normal random variable. Now, remember I said that previously that normal distributions are everywhere, but for one thing, the standard normal can take negative values, and that wouldn't always make sense for us. For example, stock prices. We might say that heights of students are approximately normally distributed, but they don't go negative, for example, right? So the other thing is approximate normals arise from sums of independent identically distributed random variables, right? If you look at the central limit theorem. Sometimes we might be interested in the products of independent identically distributed random variables. And the product of the standard normal doesn't help us with that. Let's consider the product of independent identically distributed random variables taking only positive values. Okay. So pi is the product of x1, x2 up to xn. The xi are independent identically distributed random variables. And let's suppose further that the xi only take positive values. Now, if we take the logarithm of pi is log of x1 plus log of x2 and so on up to log of xn. So if the xi are independent and they're identically distributed, then the log of xi, these are new independent random variables, which are independent and identically distributed. And so for a large enough n, the central limit theorem says that log of pi will behave like a normal random variable. Okay, so if x is a random variable which takes positive values, and the random variable y equals log x is normally distributed, then x is said to be log normal. So supposing that x is equal to e to the y, where y is normal, then log of x is y, which is normal. So x is said to be log normal. So normal random variables have two parameters, mu and the variance. And supposing that x is log normal, so that y is equal to log x, and y is normally distributed with mu and sigma squared, then the standard random variable, the standard normalism, z is equal to y minus mu over sigma, right? So then y is equal to sigma z plus mu. So x is log normal, and then this y, which equals log x, is equal to sigma z plus mu, where sigma would be the related standard deviation and mu would be the related expectation. Okay. Then when you exponentiate, you get x is equal to e to the y is equal to the mu plus sigma z, where z is the standard norm. So we, in some applications, especially in finance, mu is called the drift and sigma is called the volatility. Okay, so if we know if we have this form for the log normal x, we'd like to find the PDF for x. So, right. So we're starting with x being log normal. That means y equals log of x is normal. And we'll suppose that y has parameters mu and sigma. So the PDF is 1 over sigma root 2 pi x exponential negative log of x minus mu squared over twice sigma squared. Why is that? Remember your rules for transformations, one-to-one transformations of random variables. Okay, you know the PDF for y, so you can find the PDF for x. Now the CDF, remember f sub x of x is equal to the integral from minus infinity to x times the PDF of the PDF, and that's the probability that the random variable x takes a value less than or equal to small x. So now if we take for x positive, the CDF will be f sub x of x is equal to 1 over sigma root 2 pi integral t equals 0 to t equals x 1 over t exponential negative log of t minus mu squared over twice sigma squared dt. Then what's the expectation? The expectation is the integral from x takes non-negative, it doesn't take any negative values. So it's the integral from 0 to infinity t f sub x of t dt. You already have your f sub x, so you insert the t in there, pull out any constants, and you make a transformation w equals log of t, and then you put that back into your exponential of expectation of x. You rewrite w minus mu squared minus 2 sigma squared w, and then the expectation, you do some workings, and you will get that the expectation of x is equal to e to the mu plus sigma squared over 2. So once again, x was log normal, y equals the log of x was normal. Normal has expectation mu and variance sigma squared, right? And then the expectation of the original x will then, in terms of those two parameters, will be e to the mu plus sigma squared over 2. Okay, if we calculate the variance, it's the expectation of x squared minus the expectation of x quantity squared. We've already worked this bit out. Okay, so we're subtracting off the square of that, and we're taking the explanation. The expectation of x squared. If we set t equal to x, then we can do the integral, and we will get then that the variance is exponential of 2 mu plus sigma squared times exponential of sigma squared minus 1. Okay, so is an example. And like I said before, this is something that's used extensively in finance. Suppose that S0 is the price of a security, S1 is the price after 1 day, Sn is the price after n days. I suppose we'll assume that prices aren't going to 0 identically. So one model for such a situation is that x to the n, which is equal to s of n divided by s of n minus 1. So the comparison of the current day compared to the price on the previous day. So one model is that for stock prices is that this should be log normal. Okay, so we look at the price of the security. We estimate that mu is equal to 0.0004 and sigma equals 0.016. What's the probability that S will be higher tomorrow than it is today? S to be higher would be that this X event would be bigger than 1. So the probability that that ratio is bigger than 1 is the probability that the log of that ratio is bigger than the logarithm of 1. This probability that the log of X is bigger than 0. But if X is log normal, then this will behave like a normal random variable. So it's probability that Z is bigger than 0 minus 0.004 over 0.016. Right, you've got to subtract off mu and divide by sigma. Right, and on here you take 0 and you subtract off mu and you divide by sigma. And then that's 1 minus property that Z is less than 0.0025. So that's 1 minus the CDF evaluated at 0.025. We look up the value of the CDF and we get 0.5, approximately 0.51. Okay, so that's one important use of the log normal random variable.